Okay, can we all do that? Wonderful. So mid-latitude cyclones, what we're doing today. The first things first, we need to recap cyclones. A cyclone is a low pressure system which moves either clockwise or anti-clockwise depending on what hemisphere you're in. If you are in the northern hemisphere, a cyclone will move anti-clockwise, so cyclonic will be anti-clockwise, anticyclonic would be clockwise. So if you can't already figure it out, an anticyclone would be a high pressure system. Okay, then in the southern hemisphere, cyclonic is clockwise and anticyclonic is anti-clockwise. So I've included two pictures over there so you can see what these systems look like in the two different hemispheres. So the one on the left-hand side there is the northern hemisphere. So that is a mid-latitude cyclone. You can see it's turning anti-clockwise, so it's one way. And then the one on the right-hand side is turning clockwise. That is in the southern hemisphere. Okay, and I also just want to point out the difference between a mid-latitude cyclone and a tropical cyclone. So right now we know that a cyclone is a low pressure system and it moves in a cyclonic direction. The wind blows in that direction. But we have two types of cyclone. The one is the tropical cyclone that we already looked at in the first video, and now we're looking at mid-latitude. So the one on the right-hand side, you'll see has a tiny little eye. You can actually see the little eye wall. That is your tropical cyclone or your hurricane. The one on the left-hand side has quite clear spiral, and you won't see any kind of an eye. That is a mid-latitude cyclone. I actually want to show you on a more global scale. Great. Okay, so here is our tropical cyclone. This is tropical cyclone Jasper in the southern hemisphere. So you can also see the way the little icon is turning. Let's just back in. So you can see which way the little icon is turning. You can see it's moving clockwise. It's the southern hemisphere cyclone. And if we can compare it, for instance, the size of that, nice clear comma or upside down comma in this case, to this. Okay. So there you can see the tropical cyclone is probably covering the size of those islands. And here you can see the cross section of this mid latitude is quite a bit larger than that hurricane. So a hurricane is a lot more destructive, is a lot more powerful, but it is a lot smaller because the energy is a lot more concentrated over a small space. Other major difference is where you find them. So tropical cyclone, you would expect to find tropics. So just to clarify where the tropics are, you can see right along the middle over here, you have the tropics. So you've got Tropic of Cancer up here and Tropic of Capricorn. And it's between these two lines that you'll find a tropical cyclone. So within the tropics, hence the name. Then the mid-latitude cyclones, when it loads, there we go. So the mid-latitude cyclone you find between the tropics and the polar area. So here we have this warm tropical air, and here we have this cold polar air, and this shaded out space over here is the mid-latitude areas. So this is the area where the warm tropical wind or warm tropical air meets the cold polar air. I want to show you what that looks like on null school. So I've just quickly changed the setting to temperature. And I want you to notice how the globe is split into these different colors. So around the middle over here, around the equator and by the tropics, it's mostly green. And then just further north and south of that, it is a blue, a light blue, and even a purple. Then these areas in between, right around here, that is your front, or your major polar front. And this is where you would find mid-latitude cyclones. Okay, so mid-latitude cyclones form usually over the uh, ocean or the coastal areas, and they will always move from west to east. I can show you that. Actually, I don't know if I'll be able to show you that. I'll try. So if I take this little curve over here as an example, you see how it's moving from west to east. I'm going to have it jump forward a little bit. Oh, that's actually a perfect example of a mid-latitude cyclone. I'm busy watching this form. That right there is a mid-latitude cyclone that's forming. And you notice how it's just moving towards, there it is. Okay. Hello, welcome back. So you won't have the same level of disaster and destruction as you would with a tropical cyclone. Okay, so what actually forms a mid-latitude cyclone is the collision of these two air masses. So towards the poles, you can see this very cold, very blue air. Towards the equators, you can see this pinkish, reddish, warm air. So we have the polar area, the polar air mass. We have the warm tropical air mass. And where they meet, we have the formation of a jet stream. So what basically happens is that this difference in temperature creates a difference in pressure. And the different pressure, or a pressure gradient force, drives very high altitude winds. And these winds are jet streams. Specifically in this case, it's the polar jet. Let's take a look at our score and see if we can see that. So you can kind of see that already. You can see that there's a lot of air movement where the green and the blue air meet there. So this is a little bit closer to the ground. You can see that the land and the continents and close towards the equator is a lot warmer. That over there. And as you get to the polar area, you have this very clear line between the green and the blue. And I'm slowly going to move up through the atmosphere. There it starts to become cooler. That's actually off. And you can see that this smooth wind formation starts to occur. I'm going to switch the animation from the temperature to wind speed. And I want you to notice how the wind speed changes. So this is quite high up in the atmosphere. Here you can see by the green that the wind is moving quite quickly. But if I move up, you can see it switches to red or almost purple. That means there's very strong winds blowing right there. Those are the jet streams. And where you find these very strong winds also changes with the seasons. So at the moment, at the moment we're in between seasons. So let's find a more extreme. So let's go to last year, June. Okay, so June, Southern Hemisphere is experiencing winter. And there you can see these beautiful ribbons of the jet streams. And northern hemisphere is experiencing summer, and you'll see that you won't have as many of these clear purple lines. Now if I switch it, not to now, I go to, let's say, January of this year, go. There you can see that you have all of these uh, deep red purple jet streams towards the northern hemisphere and not as much in the southern. Okay, those are the jet streams. They are very high up in altitude. So they're very high up in the atmosphere and they're moving incredibly fast. So to kind of put into context, I'm going to click on a random point over here, and right over here you can see the speed. That's 206 kilometers an hour. So these jet streams are moving incredibly fast, so fast that it can, so fast and so powerful that it is changing the atmospheric condition on the surface of the Earth. So a jet stream is a very strong westerly wind, very high up in the atmosphere, and would usually be at least 110 kilometers an hour. But as you saw from that null school simulation, that's not necessarily a norm. That random one that I clicked on was 200. Um, Actually, I went a little bit. So what triggers a mid-latitude cyclone from forming or to form is a disturbance in the polar jet. When there is a disturbance in this jet stream, it will lead to a disturbance on the ground and a disturbance in that front. There you can see the jet stream, and it's creating this little wave-like formation. And that wave formation creates a disturbance in the temperature closer to the surface of the Earth. Show you. There it is. There is a little bit of a wave. That is from the movement and the bending of the jet stream. Which brings us to our stages of development of mid-latitude cyclone. So the initial stage is also referred to as stationary stage. That is where your two air masses are just sitting opposite each other, not really moving, and the wind is blowing parallel to each other in opposite directions. So the cold air mass is facing the warm air mass, the polar air is facing the tropical air, and the wind is just blowing in two different directions. Because they are so different in density, the air won't just mix. Then when we have that disturbance in the jet stream, you will have some bending that starts to happen on the surface of the Earth. So some bending will start to happen with the two fronts. You'll have a low pressure that begins to form. So the low pressure forms when the wind is blowing in a clockwise direction. Okay, so there we can start to see a little bit of a wave, a bit of a wobble in this diagram. Let's see if we can see it on, well, okay, so this is, I think, as close as we're going to get to some kind of a stationary front. So you have the wind blowing parallel to each other, you have the warm air over there, you have the cold air over there, you have a little bit of a disturbance starting to form, and the jet stream or the front starts to form a little bend. So that's your early disturbance. When it has developed enough, it will reach the mature stage when you can clearly see the cold front and the warm front. The cold front will always be behind the warm front. Here it has finally moved to a mature stage. I can recognize it kind of has like a shark fin shape. This line over here, separating the blue and the green, would be a cold front. Behind that cold front is cold air. In front of it is warm air. This line over here, where the blue is on the right and the green is on the left, that line would be a warm front. In front of it is cold, behind it is warm. So your polar front forms a cold front, and the tropical air forms the warm front. Where your cold front is, you will have very cold weather and you'll start to experience rain. Where the warm front is, you'll experience very warm weather and probably some clouds with light rain. On the ground, you refer to this as the warm and the cold sector. So, what happens when the cold front finally catches up to the warm front? You get a occluded front. When they catch up to each other, they will start to occlude. The cold air is denser than the warm air. The cold front with the cold air will come in and scoop up the warm air and lift it into the atmosphere. So you can kind of see that starting to form on this diagram. You can see how the cold air is scooping around and picking up that warm air. So you'll notice that these maps always use these similar kind of symbols. A cold front will be marked with little triangle shapes. A warm front will be marked with little semicircles. Where they're occluded, the two symbols will overlap. So you have triangle, semicircle, triangle, semicircle. Oops, yeah. And when it has been completely occluded, it will reach the degeneration or dissipation stage. That is when all of the warm air has been lifted and cut off by the cold air, that it's not on the ground anymore, and you just have the cold air mass on the ground. That is the dissipation stage. At that stage, the pressure starts to balance out and the low pressure cell will disappear. The weather might still be cloudy and rainy, but at this stage, it is leveling out and okay, so let's just take a look at the weather conditions at each of these fronts. Where there is a cold front, the temperature will decrease as the cold front passes over it. So remember, it will be warm before the cold front reaches it. It's warm, comes the cold front makes it cold. Yeah, the pressure will decrease as the cold front approaches and it will increase again as it passes. So the warm, moist air is lifted by the cold front, causing it to cool and condense. So let's take a look at this diagram over here. I think this is a really nice animation. There you can see my reference over there, the Thomson animation. So you have the warm air mass over here, and the cold front starts cutting in and scooping up that warm air. And as it scoops up that warm air, it pushes it up in altitude, forcing it to condense. When it rises, because it rises so rapidly with the cold air, it will form these very big clouds, usually cumulonimbus clouds, and it can also have accompanying thunderstorms and massive rain. So you can see over here, we've got the warm air being forced to rise up. We have cumulonimbus clouds that are forming over here. We have massive rainfall and really cold conditions around. I'm not going to explain too much about the backing and the veering, but as the cold front would pass over, in the southern hemisphere, the wind would start backing, and in the northern hemisphere, the wind would start veering. What that means is that where you perceive the wind to be coming from changes direction. The wind will still be moving in a cyclonic direction, but where the cyclone is relative to you will be somewhere else. So it will seem like the wind is blowing from somewhere else. That's my nutshell of backing in. Okay, then we get to warm front conditions. Temperature will increase as the front passes over. So the air in front of the warm front is cold. The warm front approaches that cold air, and behind it is then warm. The pressure will decrease when the warm sector arrives, and the humidity will increase. Okay. Warm, moist air is lifted to form clouds, and a gentle pressure gradient. Pressure gradient means a difference in pressure, and I'll show you now what I mean by gentle pressure gradient, but it means that the air is lifted very slowly. Remember that the warm front moves a lot slower than the cold front. So it won't have that sudden cloud formation, it won't have that massive rainfall, and it doesn't have these same violent, massive clouds. This is a lovely diagram that shows what I mean. Here you see you have this gentle slope up. That is the warm front. So over here we have cold air that's being pushed back, the warm air that is slowly crawling over that cold air mass. And as it crawls over it, as it slowly rises over that air mass, it gradually condenses to create these different types of clouds. So you would expect to see stratus clouds, nimbus stratus, altostratus, cirrostratus, and clouds. If there is rain, it'll be very gentle, very prolonged rain. So anything from nimbus stratus, stratus. And then we finally get to our occluded front. So you can kind of see it over here, how I've got my triangular cold front and my semicircle front that meet. So this is where the cold front has finally caught up to the warm front, and it's lifting it off of the ground. So that is where the occlusion happens. But we have two different types of occlusion. We have a warm occlusion and a cold occlusion. Warm occlusions and cold occlusions are like, you can think of them as milder versions of a warm front or a cold front. So what has basically happened is that you have this line of cold air, and the cold air has come and scooped the warm air off of the ground. But where it has scooped it off, even though it is just completely cold air on the ground, some of the air might be colder than the rest. And that will create its own type of front. So if the air in front of the warm front, so this side, is warm, you would have a warm occlusion. If it is the other way around, oh, sorry, there we go. So I want you to notice that in both cases, you have cold and very cold. You have the warm air that has been lifted off of the ground, but you have two different types of cold air. This now becomes the new cold front, and this becomes the warm front. Not actually, they're both still cold air, but this is just colder. So the whole formation kind of looks a bit like a cold front. I'm going to go back to that earlier diagram of the cold front, and you'll see what I mean with that little curved wall. There. So I want you to notice this shape over here, curved shape right there. You have the warm air that's coming and rising up over it like that. Back to the cold occlusion. There. There's that same curve. And the warm air is rising up that cold air. Remember, by warm, I just mean warmer. The actual warm air has already been lifted off the ground. And then if I compare the warm front over here, sorry, to the warm occlusion, you'll see that same little slope, that gentle incline, similar to when we had the warm front. Okay, so for a warm occlusion, air ahead of the cold front is colder than the air behind it. The air rises and forms in stratus clouds and rain. The weather will be similar to that of a warm front. So notice it again. There it has a gentle incline. There it is cold. And there it is just cool, technically warm. Then by my cold occlusion, the air in front of the cold front is warmer than behind the cold front. If I take it back here, this is cold, but this is very cold. Okay, so it mimics a cold front. The air rises and forms stratus clouds, and yeah, and then the cold occlusion is similar to a cold front. I know that the part about occluded fronts can be quite complicated, but I hope that I have gone through it as simply as possible. It does take some time to wrap your head around the fact that you have cold air and cold air, but it's somehow a warm occlusion. You can really just think of it as a mini version of a warm front. Not actually a warm front, but it mimics a warm. Okay. Now we're going to look at how this impacts us in South Africa. So in South Africa, we have rather unique climate in that the Western Cape only actually gets frontal rain. So the only way that the Western Capes get any rain is from these mid-latitude cyclones. So the southern tip of South Africa is just within this region of reaching the mid-latitude cyclones. But they only actually travel up north when we have winter. During summer, all of the systems move south, so because the sun's direct rays is more south, so all of the atmospheric circulations south. So the mid-latitude cyclones are also further south. In winter, the sun's rays is more focused on the northern hemisphere, so the mid-latitude cyclones move slightly more north and they reach South Africa. Here you can see what I mean by the little triangle pointy parts. So that is your cold front. That means that it's moving towards South Africa, it's moving towards the Western Cape, and it's bringing cold weather with it. So cold weather, rain, all of that delightful winter conditions. Over here is your warm front. You can see the little semicircles, which means that everything over here would be warm. There it is cold, there it is warm, there it is cold. And this is what I mean by the cold air is on both sides and it comes and it scoops it up. I can do a separate session on how to interpret weather maps. I just thought it was worthwhile including one so you can understand what I mean by the mid-latitude cyclone would reach the Western Cape. Okay. Are there any questions from your side? Oh, what happens with the Berg wind? That is really interesting. So Berg winds are very, very popular topics around the Western Cape when it comes to rain. A Berg wind will come in just before a mid-latitude cyclone. So the two processes are actually linked. Wondering if I can show to you there. So here you can see what I mean, that inland it is very warm. You can quite obviously 43 degrees for whoever's living there. I'm so sorry. Okay, so inland it is very warm, and when it moves in this clockwise direction, it's pulling that air from inland towards the coastline. So one, that air is warm. That's why a Berg wind will actually feel warm. But the other reason why it's warm is also how it gets its name. It has to blow down the plateau. Let's see if I can find a map of South Africa. Oh, that's a bit better. So inland South Africa is quite high up on a plateau. It's not very clear to see on this map, but that is much higher altitude than anything over here along the coastline. So when the wind is pulled from inland towards the ocean with this incoming mid-latitude cyclone, with this incoming cold front, and then it pulls that air in, it pulls in this warm, dry air, but it also comes tumbling down these mountains. As it moves down the mountains, it's experiencing a change in pressure. It's being placed under more pressure because it's moving down the altitude. And as that happens, it actually gets heated up. It comes down this altitude, it comes down the mountains already warm. It experiences more warm because it's changing pressure, and then it blows over the Western Cape and Cape Town area. Usually, when that happens, people will recognize it immediately as this very warm, very dry wind. And it is a telltale sign that there's a mid latitude coming, a cold front coming, and usually within the next 2 to 3 days, you will have some kind of rain. And then it suddenly gets very cold. So, berg winds can actually be a bit of a hazard as well. So, because they are so warm and dry, they can lead to fires. The berg winds aren't just a heads up that there's rain coming. It can be something of a hazard to those surrounding farms. And I hope that you possibly learned something interesting or that this might help. Have a lovely day and thank you very much for joining. I hope to see you again next week. Cheers.